Forces, Part 3. Here are your priming questions. Forces, Part 3. The next series of videos will go through a number of practice problems, and I'm going to be using these practice problems to bring up new concepts, things like summation equations, net force, acceleration, and we're going to apply all of them through the use of these practice problems. So please pay attention and see when new things are introduced. Alright, so a net force of 2,300 newtons is applied to an 820 kilogram object. What is the acceleration? Now for some of these, you might want to pause the video and then check to see if you get the right answer and then go through the rest of the video, but it's up to you. Alright, so for this one we are given the net force, so you know our equation as F equals ma. That's going to be the net force is equal to the mass times acceleration. So in this case, we know our net force is 2,300 newtons, and that's going to be equal to the mass 820 times A. When you work this out, you get 2,300 divided by 820, and that's going to give you an acceleration of 2.8 meters per second squared. And that's it. For number 2, what net force is required to stop a 1,500 kilogram car from a speed of 110 kilometers per hour within a distance of 55 meters? For this one requires quite a bit more work, and it makes you look at your units more carefully. If you think of the standard units that we're using, we want to stick with our base units. So that means that when we're talking about any sort of displacement, we're working in meters. And anytime we're talking about any sort of time, we are going to want to be in seconds. So what that should automatically tell you is that for this 110 kilometers per hour, we want to convert that to meters per second. And so let me quickly show you how to do that. If you've forgotten, you do want to know how to do these. So you have 110 kilometers over 1 hour, and we want to convert our kilometers to meters. 1 kilometer is equal to 10 to the third meters, and then we can do our time. So we have hours to cancel that out to minutes, and then minutes to seconds. And we start filling this in. And there we go. When you work this out, you should get 31 meters per second. Now, since we've done that conversion, we need to start thinking about what is given to us and what we are asked to find. That's how we should approach any of these practice problems. And so we are given the mass, and so let me expand the page a little bit. We have the mass of 1,500, right? Yeah, 1,500 kilograms. We are given this distance of 55 meters. And this velocity is the initial velocity. We are looking to see how much force is required to stop a car from a speed of 110 kilometers per hour, which for us is going to be 31 meters per second. So we know our initial velocity is 31 meters per second. And we also know our final velocity because the car comes to a stop. So our final velocity is going to be 0 meters per second. And so now we use our kinematics. We see that we have our D, our V naught, and our VF, and we have our M. What we are looking for ultimately is our force. And if we start linking all of our variables and our equations together, our force and our mass use F equals ma. The thing is, we don't have our A. And so we need to find our A. So that means we also need to look for our A. And so now, if we think back to our kinematics, we're looking for our A, we have our VF, we have our V naught, and we have our D. We have an equation that relates all of these together. It is VF squared is equal to V naught squared plus 2AD. We plug in our values here, so we have 0 is equal to 31 squared plus 2A times 55. When you work this out, you get negative 31 squared is equal to 2 times 55 times A. And when you solve this, you should get an acceleration of negative 8.5 meters per second squared. The negative simply shows you that it's going in the opposite direction. It is slowing the car down. All right, let's go to the next problem. An astronaut with a mass of 75 kilograms travels to Mars where gravity is equal to 3.8 meters per second squared. What is his weight on Earth? If you remember from one of the earlier videos, weight is simply a force, and it is the gravitational force. So in this case, we can think of our F equals ma equation as weight is equal to the mass times gravity. And so, if we're simply looking for the weight on Earth, we say weight is equal to his mass, which is 75, times 3.8, which gives us 740 newtons. So this is his weight on Earth. If we're looking for his weight on Mars, we're given the G value, the G constant for Mars, where it's 3.8 meters per second squared. And so we can do the same equation. Weight is equal to the mass times gravity, which is going to be equal to 75 times 3.8 for Mars, which gives us 290 newtons. So this is the concept of weight. Weight is equal to the mass times gravity. And for the last problem here, what is the value for G on top of a mountain if the same astronaut weighs 683 newtons when at the top? So in this case, we are given the weight and we are asked to find the value of G with the same mass. And so we can start with the same equation. Weight is equal to the mass times gravity. And now we have 683 newtons is equal to 75 times G. And so our value for G, the acceleration due to gravity, is going to be 9.1 meters per second squared. The further up you go, the smaller the G constant becomes. The 9.8 that we're using right now, this is going to be at the surface of the Earth, and it will be pretty good for us for almost all of our calculations. For the next problem, a car moves forward at a speed of 40 meters per second. The car's engine applies a force of 4,000 newtons. Wind resistance and friction oppose the car with a force of 4,000 newtons. Draw a free body diagram. Then, what is the net force felt by the car? And C, if the car's mass is 4,500 kilograms, what is its acceleration? So, let's draw a free body diagram first. And so, free body diagram, we start with a box. And now we need to start adding our vectors onto this box. And if we look at this, we are told that it moves forward at a speed of 40 meters per second. The car's engine applies a force of 4,000 newtons. Let's say that this car is traveling to the right. And so that's going to be our positive direction. The car's engine will apply a force of 4,000 newtons to the right. And let's go ahead and just write that in. So this is going to be 4,000 newtons. We also know that wind resistance and friction oppose that, and so it's going to be in the opposite direction with 4,000 newtons as well. What we're missing right now is the gravitational force, the weight. And so, if we go ahead and look ahead and we use the 4,500, we can say that we have a vector that's going down, the gravitational force going down, and this is going to have a magnitude of the mass times gravity, which we'll just say 4,500 times 9.8. Now, if we stopped here, this would be an incomplete free body diagram. What this would show is that we have a net force going in the down direction and that our car is actually accelerating towards the center of the Earth. That's not happening in our problem, and so we need to make sure that we show the last vector here, which is again what we call the force normal, or the normal force. And this one, in this particular case, is going to be equal to our weight. So this is also going to be 4,500 times 9.8. And so here we go. This is our free body diagram, and if we were to work out our weight and force normal, this would be 4,500 times 9.8, which gives us 44,000 newtons. So this would be 44,000 newtons. And this is our free body diagram. So that's part A. Part B, what is the net force felt by the car? Now, this is where I want to talk about what we call summation equations. And this is when we use sigma. So sigma F means the sum of all forces in a particular direction. So we can say sigma F in the X and sigma F in the Y. So we can do the sum of all forces in the X, and then we can do the sum of all forces in the Y. And then we can go back to vectors, and we can make a triangle and go from there if we need to. If we look at this, the sum of the forces in the X, this is going to be, if we say to the right is our positive, we have 4,000 newtons. And then we have negative 4,000 newtons. And so the sum of our forces in the X is going to be equal to 0. If we look at the sum of the forces in the Y, we have 44. Actually, before we do that, let's assign a positive direction. In this case, let's go ahead and say up is our positive direction to make it easy. So we have 44,000 for our normal force. And then we have 44,000 for our gravitational force. So again, the net force is going to be 0. So the net force acting on this particular car is 0. For C, if the car's mass is 4,500 kilograms, what is its acceleration? This is when we use our F equals ma equation. And this F we can think of as our net force, or the sum of all forces. And so the value that we get from the summation, we can plug into the F. And so the sum of all forces in the X, let me just rewrite this with a different color down here. If we do the sum of the forces in the X, we found that to be equal to 0. That's going to be equal to the mass times acceleration, which is going to be equal to 4,500 A. So 4,500 A is equal to 0, which means that our acceleration in the X is going to be equal to 0 meters per second squared. We can follow the same pattern for the sum of all forces in the Y, and we found it to be equal to 0 again, and that's going to be equal to the mass times acceleration. So we can say 0 is equal to 4,500 A, which tells us that our acceleration is also 0 meters per second squared, which means that our car is not accelerating. Now here's where we want to pause for just a moment. You want to be careful with your understanding of zero acceleration. In this case, our car is still moving. It's simply not accelerating. If we look back up here, it is moving forward at a speed of 40 meters per second. We found that the acceleration is 0 meters per second squared, which means that there is not going to be any change in this particular velocity. You want to be careful. Sometimes, many students will think that the zero acceleration, 0 meters per second squared, means that the object is at rest. It could be, but not necessarily. 0 meters per second squared, what you should think about is it tells you that it is a constant velocity. Whether that velocity is 0 or another value depends on the problem, but it simply means a constant velocity. For the last problem now. The following sign, this coffee shop sign, has a mass of 11 kilograms. What is the tensional force on each of these cables? And these cables are equally spaced. So if we were to work this out, we want to draw a free body diagram. And so we draw our free body diagram. You can just do it right below. And now we want to begin applying our vectors. One of the first vectors that we typically want to try to remember to put on is our gravitational vector. And this vector is going to be the weight, which is going to be equal to the mass times gravity, which is equal to 11 times 9.8. 11 is the mass, 9.8 is the gravitational acceleration, and this is going to be equal to, where is it? 110 newtons. So we know we have a 110 newtons going down. And now we don't know the value of the tension of these two cables, but we know that we have two cables going up. Oop. And this is off kilter, so let me fix that. We know we have two vectors going up, and in this particular case, with the way these two vectors are, with these two cables, we know that they have the same tension. So we can say that these are both force T, the force of tension. So we have two force of tensions going up, and we have the weight going down. So now, if we wanted to make a summation equation, we can first start with what's easy, the sum of the forces in the x, and we know that it's 0. There aren't any vectors in the x. So we already know the sum of the forces in the x is 0. And so let me go ahead and move this out of the way. And now, we can work with the one that actually matters for us. The sum of the forces in the y is equal to... Now, we need to set a positive direction before we start listing these out. Let's go ahead and say that up is positive. And so, our positive vectors, I default to listing positive vectors first. We have two ft's, so ft plus ft. And then we have minus the vector that's going down, 110. And that's going to be equal to the mass times the acceleration, which in this case isn't moving. So what that tells us here is that this F equals ma. For this ma, we can replace this with a 0. What this 0 tells you, and along with this 0, is that this object is in equilibrium. Equilibrium means that there is no net force acting on the object, and that the acceleration is 0 meters per second squared, and that the velocity is constant. In this particular case, with this sign, our constant velocity is 0, but it won't always necessarily be like that. And so when we start working out the math for this, we can combine these two together. So we have 2 ft's minus 110 is equal to 0. So 2 ft is equal to 110, which means that each tensional force is equal to 55 newtons. And there you go. So some of the main concepts from this presentation. Equilibrium means 0 acceleration, which means constant velocity, summation equation, and net forces.